we shall continue from where we had left in the last lecture on the discussion of AlGaN GaN RF HEMT. We concluded the lecture with a discussion on the gate lag and the drain lag and the effect of silicon nitride passivation in that same. So, we will start from there and we will also go into understanding what properties of device or material help us make a better gallium nitride power amplifier from the device point of view. Okay, that is also something we should discuss in this lecture. So, what is the whiteboard here? So, if you recall, we discussed about the gate lag and drain lag, and I told you that the passivation plays a key role. Okay, but apart from passivation, the buffer also plays a key role. So, this is your AlGaN, this is your GaN, and you have a 2D electron gas here. Okay, there is a gate here, there is a drain here, for instance, the source here. So, as I told you, there is a silicon nitride passivation layer. Okay, there is a silicon nitride passivation layer, and when you have a higher voltage on the drain as well, say 30 volt, your field lines, the field is the highest at this point in the gate drain edge, and the field penetrate like that. So, what happens is that this buffer layer, the field lines reach the buffer layer, the electric field reaches the buffer layer, and in the buffer layer you have iron doped iron atoms. So, the field will reach the iron atoms. What will happen is that the trapping or releasing capturing electrons by this acceptor like states, say iron atoms or carbon atoms, that will kick in. So, it will lead to collapse of the current. It will lead to collapse of the current in the drain lag. Even if your silicon nitride is the best silicon nitride, the surface states are being taken care of, but still the drain lag or the gate drain double pulsing, the collapse under that is a function of both the surface as well as the buffer. So, not only the surface has to be good, the buffer has to be good. By the buffer it has to be good, it means the crystal quality has to be really good with as low dislocation, point defects, etc. And the iron dope layer should be far from the 2D electron gas. It should not be very close, because the iron doping will have a tail. The distribution of the iron, although you stop the iron doping here in MOCVD especially, the iron doping will have a tail distribution, it will stretch outwards to some extent. So, you want the iron dope layer to be as far below, at least a few hundred nanometer, 500 or 400 nanometer, so that the iron doping atoms, the iron atoms are actually not, they do not feel the field when you pulse under high drain gate double pulsing. Otherwise, they will start capturing, releasing electrons up at the pulses, and that will lead to the collapse. So, that is a very important part, and so it is a trade off. You cannot keep it very far, because then your leakage will increase. The whole purpose of having the iron atoms is to reduce the leakage. So, leakage has to be reduced, but it should not be very close to the 2D electron gas channel in the interest of not collapsing the current further. Buffer induced collapse, this is a buffer induced collapse, this is a surface induced collapse. So, this is a very important property. So, the buffer and the surface both are important. Now, the passivation layer I told you, but there are two ways to do. People sometimes do gate first process after source drain, I mean, and this thing. So, you put the gate like that, correct, and after that this is AlGaN, and after that you have the silicon nitride. The silicon nitride layer could be around say 200 nanometer thick, and then there has to be a field plate. The field plate has to go something like that, and there are different designs of field plate. This is a gate connected field plate, because this is connected to the, this is a dielectric, of course, the field plate dielectric and the passivation layer is also there, but this gate field plate is connected to the gate outside the mesa area. So, in the top view if you look, this is your gate pad, this is your gate finger, this is your drain, this is the source. Okay, you have a dielectric covering everything, and then you have a field plate that goes on top of the gate towards the drain, something like that, right. That is what is happening. The drain, it extends towards the drain. We discussed the concept of field plate when we discussed AlGaN gas HEMT anyway. So, I am not going to discuss the physics of a field plate, but you know that field plate is like that, and so this field plate will be connected. For instance, this is the mesa area. Outside the mesa area, field plate can connect metallically short the gate. What I mean is that if this is your gate finger, you can have a via in the gate, and the field plate metal could be touching the gate, and then there is a dielectric separating this. This is your gate, this is a dielectric, and this is a field plate. So, the field plate metal could be nickel gold, for instance. It is going over the gate, but it is metallically shorting the gate outside the mesa, maybe here you are shorting, or maybe you can short here. So and then it is touching. So this is a gate connected field plate, you etch and do it, but then this is a gate first, but you can do even gate last or gate second. I am talking about only in the context of silicon nitride passivation. What people do is that this is also widely adopted in industry, by the way, the gate second process is that after you have source drain, for instance, this is your AlGaN, this is your GaN. What you do is that you put silicon nitride everywhere. Okay. Then you do lithography and you open up a little bit of silicon nitride here. Okay. So how it will look like is that it will look like this. This is silicon nitride, okay. This is silicon nitride. Now you spin coat photoresist, correct? You spin coat photoresist and you define something like, say, photoresist is here. You define an opening like that. This is photoresist, PR, okay, organic material, you know. Then you can deposit a metal now. Now you can deposit a metal, something like that. It will come like that, okay. This is a metal, this is nickel, gold maybe, and you remove the PR now. So how people eventually look like is that, you know, this will look like is that you have AlGaN, you have GaN, and then you have a layer of silicon nitride like that, and then finally on top of that you have a gate like that. This is like a T gate at a simple scale, okay. This is your gate. So the gate already has an extension towards the, this is the drain, right. So this part acts as a self aligned, because it is already aligned, you do not have to do an extra field plate. It is like a gate connected field plate, gate CFP, gate connected field plate, GCFP we call it, okay. So the gate connected field plate is already there in the gate because you do not have to do anything extra. Now you again put a field plate dielectric, now again silicon nitride, another layer of silicon nitride will come, another layer of silicon nitride, maybe 200 nanometer, and this is source, right. From the source you take the metal which goes up this like that and it will goes up to there. Maybe I can use a different picture here. So this is AlGaN, this is GaN, you had silicon nitride, and then you had a gate. Of course, this design, you can design this, you can run experiments, you can do Silvecos or, you know, Centaurus TCAT simulation and you get something like that, okay. This is your gate. Now you put another layer of silicon nitride dielectric, okay, again 200 maybe nanometer, and now the source, you connect the source metal, okay, you connect the source metal on top of this, goes towards the drain like that. This is your source connected field plate, okay. Source connected field plate comes like that. So this also helps in reducing the peak electric field here, reduces the electric field peak and in this region, okay, and that helps improve the breakdown further. It helps improve the breakdown further. So the source connected field plate comes like that. Again, in the top view when you see, you know, if you have a source like that and if you have a gate finger like that, then the source, you can open the source here and here, and the source can, for instance, feed in metal line like that, and then the metal could go like that, okay, metal could go like that. So there is a field plate and there is a metallic short here connecting. You do not want everything to be, because it will increase the capacitance, you only have this, okay. So this is a source connected field plate, and the source connected field plate can come even, you know, deeper. I mean, there are many designs, there are so many designs, double field plate, triple field plate, step graded field plate, sunken field plate, slant field plate. There are many designs of field plate, but that is, you know, research level, but industry also adopts whatever they think is both advantageous from the performance point of view, advantageous from the point of view of the cost, economy, etc., etc. So this is in a nutshell the fabrication process, okay. This is in a nutshell the fabrication process, but it is not very simple, by the way. Each of these process needs rigorous optimization. As I told you, contact resistance, to bring the contact resistance down from 0.5 to say 0.3 or 0.2 ohm millimeter is an enormous, it requires an enormous effort. People can do things like regrowth, for instance, okay. When I say regrowth, I mean to get to really low contact resistances, if you have AlGaN here, this is GaN. What people do is that they etch away this part, okay, and then they put the in plasma they will etch away this part, and then they will put the material back in a they will put the material back inside the MOCVD or MB, and they will grow this part, okay, and they will grow this part with extremely highly doped N plus gallium nitride, very highly doped, okay, N plus gallium nitride. So, this forms a contact sidewise to the 2d electrons, okay, and the metal will come here. This is drain metal, this is source metal. So, this is extremely low contact resistance with this is very highly doped, and this forms a contact here. So, with this approach this is called regrowth regrowth of N plus GaN region, right. This helps you bring down the contact resistance to 0.1 ohm millimeter or even lower, and this is amazingly useful and helpful to go to really high frequency millimeter wave application, Q band, W band, etc. Okay. So, this is a very important thing. So, for instance, contact resistance reduction itself could be a very process intensive and effort intensive thing, and then you have gate, then you have passivation, then you have field plate, then you have another passivation, there is another field plate, there is many process steps. So, it is a very complicated and a very expensive resource intensive development that people have to undertake, and you have to understand the physics of the same as well as the process concerns also of the same. Now, after this is done, it is not so simple. You have to measure and characterize the device, that is a different ball game. So, when you do on wafer measurement, what it means is that you need to measure the device on the wafer without dicing or packaging the device or without making an amplifier or a board, then you need something called coplanar waveguides. Now, people from the antenna background they generally think of coplanar waveguides in a different way. They according to them, coplanar waveguides or CPW is something that you design with a lot of simulation and things like that, but for our case it is most likely a metal pair that is coming in to feed the signal. So, what I mean is that if you have suppose a transistor and you have a gate, okay, what you have is that you have a drain contact here and you have source, here. The source is the ground, by the way, and this drain is the signal. The gate is also the signal. This is the incoming signal and this is the outgoing signal, correct. So, your CPW pad refers to the fact that you need to have design something like that, so that you have the probe tips that come up are something like that. This is a probe, a manipulator, and the probe tips will come up something like that. So, this is ground, this is signal, this is ground. Similarly, the probe tips will come like that. This is on wafer measurement, okay. This is again ground, signal, ground. We call them GSG probe tips, okay, ground, signal, ground. And this is a coplanar waveguide. I mean, this entire thing that is feeding in here is a coplanar waveguide. Again, this is the nomenclature we device engineers use, but how does this part look like in this case? Okay, I use this diagram, but this is not anything like what we have discussed till now, but this is useful for on wafer RF characterization. Okay, this is useful for on wafer RF characterization. So, how does the device look like there? Of course, there are different topologies, of course, but you can use what you can do is that you have a source, you have a drain, you have again a source. The gate will be here, closer to the source, away from the drain, closer to the source, away from the drain, correct, and then you have a gate pad, correct, and you define the mesa isolation as this. This is your active area, correct. Now, you do the silicon nitride everywhere, by the way, field plate, source field plate, drain field plate, passivation, etc., everything is there. So, you have to etch the silicon nitride selectively from region, say this region. You etch the silicon nitride, so you expose the source metal below, metallic shot, and you put another metal coming up here, okay, another metal come up here, you open this for instance, and the metal could pad up like that. Okay. So, essentially this is your source CPW pad. Okay. Similarly, you open up a pad like that here, you etch the silicon nitride so that you expose the source metal below, and you deposit another metal to touch it metallically short so that there is a CPW pad here like that. And from the drain side, you of course take the drain out here, the gate side is up to here. So, you have the CPW pad that I was talking you, if you remember, you know, this is the signal, this is ground, this is ground, ground signal ground, this is your probe tip. Similarly, ground signal ground, this is the probe tip. That is how you do an RF characterization. Okay. Why this elaborate arrangement? Because RF are electromagnetic waves. So, there will be incident wave, there will be reflected wave, and then there will be transmitted wave. You cannot escape this description. So, because of this way the electromagnetic waves behave or the RF waves are behaving, you need this coplanar waveguide to measure on wafer devices. Actually, when I say coplanar waveguide, this is a type of waveguide. There are many other types of waveguides. Okay. There are many other types of waveguides, transmission lines, you have microstrips, you have strip lines. These are different methodologies. For instance, you can have a dielectric. On the top of the dielectric you just have a signal, and the bottom of the dielectric is your ground. This is one type. There could be a dielectric, there is a metal, and then there is a dielectric above also. Okay. This is a metal here, signal, there is dielectric above, dielectric below, and then the bottom is ground. So, there are different definitions, one of them is called strip line, one of them is called microstrip, they are different things, but coplanar waveguide is what is used in transistor because it has this ground signal ground. It is a type of waveguide, it is a type of waveguide. And if you look actually like a waveguide, like a cable, an RF cable. So, you have a cable like that, which is actually the outer is the ground and inside is the signal that goes like that, right. So, if you take a slice out of that actually, and you think of or you imagine that you are planarizing the thing, then this is precisely what it is. This is the signal, on both sides are the ground, you know, both this is a ground, inside the signal. So, you are kind of slicing an RF cable, you imagine you are planarizing it. So, you have a signal in between and a ground on the both sides, okay, ground signal ground. Okay. So, electromagnetic waves and the basics of that will also be, we will try to cover towards the end of this course, where we understand that electric field and magnetic fields are oscillating, they reinforce each other, okay, and there could be TEM mode, TE mode, TM mode, hybrid TEM modes, etc. So, in this case, for instance, always you have to imagine that in this planar device like an FET, a part of the electromagnetic wave will also exist in the air on top of the device, part of them will exist below this laptop or this whiteboard surface in the gallium nitride layer. Okay. So, essentially if you think of this is your gallium nitride AlGaN thing, then electromagnetic waves, you know, could be like that, correct. It depends on whether it is magnetic or TEM or TM. So, some part of that is in gallium nitride, some part of that is in air, correct. So, it propagates along this direction, correct, along the sea. So, essentially you are bringing electromagnetic waves in the RF frequency range from the air, you are coupling them to an antenna, you are bringing them down to a semiconductor substrate, where all the things like power amplification, attenuation, filtering, oscillation, mixing, etc. happens at the semiconductor chip level. You are forcing an electromagnetic signal to come and couple to the semiconductor chip and implementing all these functionalities on the semiconductor chip. So, it is a complex mix of device physics, electromagnetics, RF circuit design, material science, electromagnetic theory, so many things are here actually, okay. It is not very easy, but typically we see the device level understanding is not very well covered. We typically treat the device as a black box in most of this circuit and system design, and this is precisely why we are talking about a device here, okay. But you have to understand that a field effect transistor, for instance, is a device where you are coupling the electromagnetic field to the ground and on a substrate, on a planar substrate, and you are propagating them. So, the effect of semiconductor material comes into picture vis-a-vis the RF propagation, okay. Things like delay, reflection, etc. everything will come into picture with respect to the semiconductor substrate that we are having here, okay. So, this is in a way where you have the actual device. However, if you want to measure higher power or higher current, you need to thicken the metal, okay. I told you, right, source drain metal was around 20 nanometer, 120, 30, 50, that is a too thin metal. If you carry amps of current, it will burn, it is a very thin metal, your metal resistance is very high. So this is your initial source metal stack, okay, in a source finger like that and a drain finger here, but you want to thicken that metal. You have to thicken the metal with something called electroplating. You have to thicken the metal with something called electroplating. So I mean you can do even e-beam evaporation or sputter deposition or something, but that's going to be more costly, and people typically use gold. Although it's expensive, it's very good metal. You use gold electroplating to thicken the metal. It should be at least 3 to 5 micron, for instance, thick metal, so that it can carry very high current. Okay, if you are looking for very high currents, few amps of current, for instance, or you are looking for very high power, few watts, few tens of watts, then you are looking at really thick metal. Okay, otherwise the source and drain will burn. Similarly, so essentially your CPW pads will have to be thickened, correct? Your source and drain fingers have to be thickened. So in this earlier picture, this has to be thickened, this has to be thickened, this has to be thickened. So everything has to be thickened, so you can sustain higher current. Okay, so that's how it is done. Now, but this is while I am talking about fabrication, it's good to talk about typical dimension used in gallium nitride HEMTs. So I told you the different things in the different dimensions of a transistor affect different properties. So what I mean is that, so this is source, this is drain, this is gate, okay, and this is AlGaN. Just for the simplicity sake, there could be a GaN cap, there could be a silicon nitride cap, okay, totally okay. This is GaN, and this is your 2D electron gas. This spacing LGD affects, it determines the breakdown. It also determines your cutoff frequencies to a large extent. Higher the spacing, lower is the cutoff frequency, correct? So that's a trade off between cutoff frequency and breakdown. Okay. This resistance, which also depends on this excess resistance, which also depends on the spacing. Higher the spacing, higher is the resistance. This also affects FTF max. This also affects your transconductance GM. GM is defined as the output current derivative with respect to the input voltage. Okay. This will also actually more than our drain access resistance, it's the source access resistance. I'm sorry, this is the source access resistance. So this affects the GM more. Okay, this affects the GM. Okay, the source access resistance actually affects the GM more. The drain access resistance will affect the cutoff frequency, of course, sure, and it will affect, of course, that means it also affects the delays, correct. So if you want to go to higher breakdown voltages, you need to increase the drain, this spacing, the drain access resistance, but you are looking at sacrificing or compromising the cutoff frequencies. Source access resistance affects the transconductance, which is related to the gain. So you do not want this spacing to be large, you want this spacing to be as small as possible within the limits of lithography or your device design, so that you do not, but it will also increase your capacitances, by the way. So you do not want, you want to keep an eye on the trade off that you are making eventually. Okay. The gate length LG is very important, extremely important. This is the intrinsic device. The gate length will define the intrinsic device. This is the intrinsic. Below the gate, this part is your intrinsic device. Everything else is extrinsic and parasitic. Intrinsic device is the true device. You cannot beat that. So this LG will decide your intrinsic delay. And intrinsic delay is the fundamental smallest delay you can get, which will affect the intrinsic FT, like the true FT. You cannot be better than that. Everything else, external parasitics, everything adds on to that. So the gate length definitely decides your cutoff frequency and your small signal cutoff frequencies. I'll come to FT and Fmax again, but we have discussed this in the context of AlGaN, but we will revisit them anyways. So the gate length is very important. Gate length, because it affects FT, it also affects the intrinsic GM. It also affects the intrinsic GM. It's very important. Okay. And the resistance of this gate metal Rg, this is the metal resistance of the gate. Okay, the metal resistance of the gate is very critical for Fmax, which is your you can say it's a power gain cutoff frequency or a oscillation frequency, unit frequency. So this Fmax is an indicator of the power you're going to get, and this gate resistance should be as low as possible in order to improve your maximum cutoff frequency. okay, Fmax, the Fmax you have to improve, okay, that affects that parameter. Of course, contact resistance has to be as low as possible because contact resistance will affect both FT Fmax and hence the delay. You want to minimize those parasitics here, okay. Now as I told you, low noise amplifier has different criteria, switches have different criteria, but dominant market is power amplifier. So in power amplifier you are looking at 3 important things. One is the output power density, watt per millimeter. Of course eventually you are looking at watt, not watt per millimeter, but we will come to that little later. You are looking at gain and you are looking at power added efficiency. If you can say this is an efficiency. These are the, and of course you are looking at cost, you are looking at heat. Actually the way you manage heat will decide and dictate all of this. So how you manage the thermal part is very critical, otherwise you will not get the optimal performance. Then it also depends on things like the epitaxial stack you have, you know, it also depends and another important things are like the die size, the compactness, etc., etc. But these three things are very important to look at for power amplifier. So we will go through each of them one by one. You can see that we talked about what affects the cutoff frequencies, we talked about the gate length, the gate drain spacing, the breakdown voltage, the contact resistance, the source excess resistance, the drain excess resistance. Of course the buffer leakage here is assumed to be negligible and the silicon carbide below, correct. There is no gate dielectric here, right, and this thickness, this channel thickness, okay, you can say this is the gate to channel thickness, right. You can say this is the gate to 2dg separation or the gate to 2dg distance or the channel distance. This will dictate the GM. If the it's very thin or narrow, GM will be high because the gate will have a superior control on the 2D electron gas. If this channel thickness is very large for some reason, okay, then your GM will be low, your gate control is getting weaker. So a rule of thumb is that if this channel thickness is suppose T, this is your T is the thickness of this channel and LG is the gate length, then typically the gate length divided by the T, which means the length of the gate divided by the gate to channel or the gate metal to the 2D electron gas spacing should be at least more than 10. Otherwise your gate control will be very poor. Gate control is going to be very poor and you will have huge short channel effects, SCE, short channel effects. Output conductance, for instance, you know output conductance, your drain current does not saturate. So if this gate length for instance is 500 nanometer, which is typical gate length for L-band, S-band and even approaching C-band, then this channel thickness should be 50 nanometer or lower. But this channel is typically 20 to 25 nanometer. So we are good, no problem. But if this LG is suppose 100 nanometer, the gate length is 100 nanometer, it is highly scaled device, maybe you are looking at Q-band, 28 to 40 gigahertz you are going to get power. You are looking at 100 nanometer gate. In that case the channel thickness of 25 nanometer is 100 by 25 is 4 and it should be more than 10, but it is not, which means if you use a 20 to 25 nanometer of AlGaN thickness, barrier thickness for 100 nanometer gate, you are going to get a terrible device. You are going to get huge output conductance, your gain will suffer, you will have short channel effect, it is a bad device, which means your gate to channel distance should be at least 10 nanometer, I mean at most 10 nanometer, you should not have much more than 10 nanometer. Now how will you do that 10 nanometer? You can either recess the gate, we talked about recess gate in AlGaN gas technology, so you can recess the gate to bring the gate metal closer to the 2D electron gas, or you can use a different material such as an AlN GaN instead of AlGaN GaN, where AlN only 5 nanometer AlN can give you extremely high charge like 2 into 10 to the power 13 per centimeter square, I told you that. So you do not have to do any recess gate. Your AlN barrier itself is 5 nanometer, it is sufficiently thin to not do any gate recess and still get an amazing gate control, except that your gate leakage will be high, so you have to try to address that, and your contact resistance is going to be high unless you do a regrowth, and making a regrowth to an AlN GaN HEMT, again this is a process complexity. So eventually everything is a trade off. How you, the process complexity, the cost and the performance have to trade off, otherwise you know that's inevitable. But in these 3 things that we are talking about, you know, P output, the output power depends on the current that you are looking at getting and the voltage at which you are biasing. The current that you are looking at depends on the 2D electron gas density, correct, It depends also on mobility, by the way, because your excess resistances, the source and the drain excess resistances, the mobility matters a lot. So a good mobility always helps you. It needs a good 2d electron gas density, it needs a good mobility, and the spacing between the gate to drain or the source to drain has to be small. If your gate to drain spacing is small, your resistance will be small and your current will be high. But the flip side is that your breakdown will be low. Your breakdown will be low, but your current will be high. So breakdown being low is not good, because then it's a trade off. You want this to be high. So this depends on the gate drain spacing. So you want to increase the gate drain spacing, and then the gate drain spacing is increasing, which means your breakdown voltage is very high. So this quantity is also very high, but then that will affect ID. So it's a trade off, how much you want to sacrifice one for the other. Okay, this depends purely on the gate drain voltage. This, you use things like field plate, for instance, to improve the breakdown voltage. You use things like iron dope buffer to reduce the leakage in the buffer. Okay, so these things like that. Okay, typically the drain bias that you apply should be less than or equal to half of the breakdown voltage. Why? Because you will have a swing. So what I mean is that if this is your ID and this is your VD, and you are looking at like that, correct? This is your knee voltage, okay, and this is a region where you are not going to get power as much, because this is a linear region. You do not want this region, and of course your breakdown will come here, could be 50 volt, 100 volt, etc. So this is the allowable swing that you are going to get in the output. This is the RF swing that you are having at the output, V output. Okay, this is a swing. So this is the drain bias. This is the drain bias, which should be half of, this is the breakdown voltage minus V knee voltage. This is the range. If your typical V knee voltage is in AlGaN HEMT is around 4 volt, it could be even 2 volt or less for a really good well designed HEMT, and source drain spacing is shrunk down, etc. Of course then you sacrifice breakdown, but in general 4 volt. If the breakdown voltage is high, suppose 100 volt, 120 volt, then you can ignore the V knee and you can just say it's half of V breakdown. Okay, but of course if your breakdown voltage is only say 30 volt for some reason, then a knee voltage will matter, 4 volt will matter, you're 26 volt. Okay, so that's important. So this is typically half of your breakdown voltage. You should bias it at less than half of the voltage, because if your breakdown is here, you do not want the cycle, the RF swing, to touch the breakdown and come back again, touch the, every time you touch the breakdown voltage, you really stress the device, and that stress leads to reliability problems, significant reliability problems. So you do not want to stress the device, okay, so much. So you want to bias it at slightly lower than half, or at least somewhat lower than the half, so that in the RF swing you do not approach the breakdown voltage. You swing such that the breakdown voltage is still further away. That way you improve the reliability. You do not subject the device to very high fields. Okay, but this is the upper limit. This is the upper limit. Similarly, the current IDS, the way you bias it is half of the IDS max. Why? Because if this is your IDS max, you cannot go beyond that, because your gate will leak. Then this is your current swing you have. This is your current swing you have. You see, current swing. This is your current swing. So you're basically biasing at here, at this point. Okay. So your load line will look like something like that. Okay. This is your load line along which you are biasing. So the maximum output power you can get is actually, because it's an RF, it's an AC, so you have the RMS factor coming in. So you have half into Vmax into Imax, which is half into breakdown voltage by 2 into ID max by 2. So it's 1/8 V breakdown into IDS max. So if you know the breakdown voltage, you know the maximum current, then the maximum output power you can get in watt per millimeter, by the way, watt per millimeter is this quantity. Okay, and this does not specify frequency. With higher frequencies this will only reduce, although it does not have a frequency dependence. At any given frequency this is the highest power you will get, practically with higher frequencies you will get lower and lower power. Okay, with higher frequencies you will get lower and lower power because your gain will also reduce. So this is the upper limit to the X maximum power you get. So you know that out of the three things that we talked about in the last slide, output power, your output power depends on these two factors, and this is what at the device level you are looking at: improving mobility, improving 2D electron density, playing with the gate drain spacing to either improve the breakdown voltage or reducing the on resistance. That is a factor that comes in. Crystal quality of course matters, leakage matters, and the knee voltage matters. Will come what defines the knee voltage also will come to the knee voltage actually is defined by the product of mobility and 2D electron gas density. So you want to improve the knee voltage, you want to make the knee voltage lower, you want to improve the mobility and 2D electron gas density. Okay. So maybe with that we will conclude the lecture today. Okay. We have covered some of the very critical things about RF, AlGaN, GaN HEMT in terms of the device operation with output power, for instance, depends on what kind of factors in the device level. We started from the last lecture where we talked about gate lag and drain lag, and we expanded upon them. We talked about many of the finer details. We will continue on this discussion in the next lecture, lecture 32 also, where we will talk about beyond what we are talking about now, what factors determine the gain, what factors determine the power added efficiency, maybe even linearity from the device point of view, from the device and the material point of view. Okay. And we will then transition to a practical device, how actually real world AlGaN, GaN HEMT devices look like. Whatever we have talked about is not how practical devices look like. These are on wafer devices with just 2 gate fingers. Okay. It is not a practical device. Practical devices are much bigger. So we will talk about that also in subsequent lectures. So thank you for your time. I will see you in the next lecture.